Swayam Prabha. Digital India. Educated India.
Welcome to lecture 30 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Simultaneous Equations Model, Introduction and Basic Concepts. Now, so far we have considered the models in which the causality is unidirectional. Why unidirectional means? On the right hand side you have a set of independent variables, and these independent variables are responsible for variation in the dependent variable which is in the left hand side. Usually we denote the dependent variable by y. So, these are the x variables which are generating the variable y, and there is no possibility of feedback. Feedback in the sense that y is not affecting x's. So, the causality is just unidirectional, it is one way causality. In many applications such models work well, but in many other economic applications you have a set of variables which are generated simultaneously. So, in those cases such models having one way causality do not work properly. For example, suppose you have data on demand and price of certain commodity, then the demand and price are jointly determined by the demand equation and supply equation. So, it is not like that price is determining demand, but demand is not determining price, or price is determined by demand, but demand is not determined by price. The relationship is not one way causality. So, in this lecture we are going to discuss such kind of simultaneous equations model. We will discuss different issues related with these models, different issues related with the estimation of parameters, related with the identifiability of the model, etc. So, now we consider simultaneous equations model. In linear regression models, usually these models involve a single equation which explains a dependent variable y in terms of a set of independent or explanatory variables x's, and then the relationship is unidirectional. Unidirectional in the sense that x's explain y, but y do not explain x's. So, this is one way causality. X is causing y, but y is not causing x's. Then in many economic theories you have a system of relationships. So, many economic theories are usually built upon system of relationships, and then in such kind of system of relationships we usually find variables which determine each other. So, in some equation you have a particular x which is determining y, and in some other equation you may have the relationship in which y is determining x. Now, we consider some examples. Say in microeconomic theory, for a particular commodity there is a demand equation and then there is a supply equation, and both of these equations involve price. Then the phenomena is explained by the system of demand and supply equations, and then price and quantity are interdependent. Means it is the quantity which determines price and it is the price which determines quantity also. So, price and quantity are determined by the interaction of demand and supply equations. So, it is not like that price is determining quantity, but not determined by quantity. The relationship is not one way causality, it is somewhat like feedback. Price is determining quantity and quantity is determining price. In simultaneous equations models, model is in the form of a set of linear simultaneous equations. So, it is not like the usual multiple linear regression model in which you have a single equation. Here you have a set of linear simultaneous equations, and these set of linear simultaneous equations, then the system is jointly determined by the set of equations in the system. So, it is not a single equation, but it is a set of equations which is jointly determining the system. Now, suppose you consider a particular equation which is explaining a particular dependent variable. Then this particular equation may involve the dependent variables of other equations among the explanatory variables. So, a particular dependent variable may work as an explanatory variable in a particular equation to explain another dependent variable. On the other hand, in some other equation, this dependent variable is determined by another set of explanatory variables which may involve some other dependent variables. So, when a relationship is a part of a system, some of the explanatory variables are stochastic and correlated with the disturbances. So, you have this kind of system in which a particular equation may involve some of the dependent variables as explanatory variables also. So, it may be possible that some of the explanatory variables are stochastic obviously, and these explanatory variables are correlated with the disturbances. Now, this creates a problem at the estimation stage, because if you directly apply the OLS procedure, then because of this correlation between the explanatory variables and disturbances, your OLS estimator may be inconsistent. So, the assumption that the explanatory variable and disturbance are uncorrelated is not satisfied, leading to inconsistent OLS estimators. Then the issue is how to overcome this problem and estimate the model, because if you directly apply the OLS procedure, it leads to inconsistent estimator. So, how to get consistent estimators for the parameters for these models. Now, here is the variables classification. In a single equation linear model, you classify the variables as dependent variable and independent variables, and these are the independent variables which are determining the dependent variable. In simultaneous equations model, the variables classification is like this: endogenous variables and exogenous variables. Now, we define endogenous variables or jointly determined variables. So, the variables which are explained by the functioning of the system are called endogenous variables, or you can say that the values of the endogenous variables are determined by the simultaneous interaction of the relations in the model. Now, remember that your model is not just consist of a single equation, it has a set of equations. Then the endogenous variables are determined by the simultaneous interaction of the relations in the model. Then you have exogenous variables. Exogenous variables provide explanations for the endogenous variables. So, this is the basic purpose of exogenous variables. just like independent variables for the single equation multiple regression model. And these exogenous variables provide explanations for the endogenous variables. And the values of exogenous variables are determined from outside the model. So, the endogenous variables are determined by joint interactions of the relations in the model or simultaneous interaction of the relations in the model, whereas the exogenous variables are determined from outside the model. So, this is the basic difference between endogenous and exogenous variables. So, exogenous variables help in explaining the variations in endogenous variables, just like what independent variables do in single equation model. Say the independent variables explain the variations in dependent variable. Here the exogenous variables help in explaining the variations in endogenous variables. So, exogenous variables influence the endogenous variables, but are not influenced by them, because exogenous variables are determined from outside the model. So, these variables are not influenced by the endogenous variables. Now, we define predetermined variables. So, exogenous variables and lagged endogenous variables form predetermined variables. Now, sometimes your model also involves some lagged values of endogenous variables. Say the value of endogenous variable at time t minus 1. Suppose you consider a particular equation at time t, and then that particular equation involves an endogenous variable, the value of an endogenous variable at time t minus 1. Say in determining y t minus 1 is also involved, or lagged value of some other endogenous variable is involved in determining y t. So, the lagged endogenous variables along with the exogenous variables form the predetermined variables. Then since exogenous variables are predetermined, so they are independent of disturbance term in the model. It is quite obvious because we are assuming that the exogenous variables are determined from outside the model. So, you may assume that these variables are uncorrelated with the disturbance term, or these variables are independent of the disturbance term in the model. So, these variables satisfy the assumption that explanatory variables satisfy in usual regression model. In usual regression model, we assume that the explanatory variables are determined from outside the model. So, these variables are independent of the disturbance term. So, the same assumption is satisfied by the exogenous variables. Then an economic model involving several endogenous variables in each equation is called the structural form of the model. So, in each equation along with the predetermined variables, you may have some of the endogenous variables also. So, this form is called the structural form, and then you may transform or you may solve this structural form, so that each equation has one endogenous variable on the left hand side as a function of only exogenous and lagged endogenous variables, that is as a function of only predetermined variables. Then this new form is called the reduced form. So, in the original model, in the original structural form, you have several equations, and the equations may involve some of the endogenous variables, and then if you transform or if you solve these equations, so that each equation has only one endogenous variable in it, then you get the reduced form of the model. Then the problem with directly estimating the structural form is that it has some of the endogenous variables also as explanatory variable, or the structural form cannot be estimated using least square procedure as it includes endogenous variables on its right hand side. And then these endogenous variables which are used as an explanatory variable or which are towards the right hand side of the equation may be correlated with the disturbance term. So, if you directly apply the least square procedure, then you may get inconsistent estimators. On the other hand, if you transform this structural form into the reduced form, then each equation of the reduced form has just one endogenous variable, and you are expressing that endogenous variable as a function of predetermined variables, and those predetermined variables are uncorrelated with the disturbance term. So, you can easily apply the OLS procedure to the reduced form, and then you get consistent estimators. So, the reduced form can be estimated by least squares procedure. Now, we consider this example. In this example, you have a wage equation which is W t equal to alpha naught plus alpha 1 u t plus alpha 2 p t plus u 1 t, and then you have a price equation where p t is equal to beta naught plus beta 1 W t plus beta 2 R t plus beta 3 M t plus u 2 t. Here W denotes the rate of change in money wage and P is the rate of change in price. So, these two variables are determined by simultaneous interaction of the model or simultaneous interaction of the equations of the model. So, these two variables are the endogenous variables. Then U t is the percentage unemployment rate, M is the supply of money, R is the rate of change in cost of capital, and U 1 and U 2 are the stochastic disturbances. So, these three variables are the exogenous variables or predetermined variables, and apart from these variables you also have intercept term here. So, intercept term is also predetermined. So, W and P are jointly dependent and may be correlated with the stochastic disturbance terms. Now, notice that in the wage equation, rate of change in prices is also involved, P t is also involved. Then in price equation, rate of change in money wage is also involved, that is W is also involved. So, it is not like that the first equation has only one endogenous variables and then all the other variables are exogenous variables or independent variables. So, towards the right hand side also you find this endogenous variable, or in second equation also you have an endogenous variable, and these endogenous variables P t and W t may be correlated with U 1 t and U 2 t. Now, this creates problem. Then you cannot directly apply OLS procedure for estimating this equation or for estimating this equation, because it leads to inconsistent estimators. Now, we try to find out the reduced form of this equation. To obtain the reduced form, in the first equation, say W t equal to alpha naught plus alpha 1 u t plus alpha 2, we replace P t by the value of P t of given in second equation, P t equal to beta naught plus beta 1 W t plus beta 2 R t plus beta 3 M t plus U 2 t plus U 1 t, and then we take this term towards the left hand side. So, you get 1 minus alpha 2 beta 1 W t equal to alpha naught plus alpha 1 u t plus alpha 2 beta naught plus alpha 2 beta 2 r t plus alpha 2 beta 3 m t plus alpha 2 u 2 t plus u 1 t, and then we solve this equation for W t. So, we get W t equal to pi 1 naught plus pi 1 1 u t plus pi 1 2 r t plus pi 1 3 m t plus v 1 t, where pi 1 naught is equal to the intercept term is alpha naught plus alpha 2 beta naught divided by 1 minus alpha 2 beta 1. So, this is pi 1 naught. Similarly, pi 1 1 is the coefficient of u t, is you get alpha 1 from here divided by 1 minus alpha 2 beta 1. So, you get pi 1 1. Similarly, you get pi 1 2 as the coefficient of R t, alpha 2 beta 2 divided by 1 minus alpha 2 beta 1, and then you get pi 1 3 also. And then we define V 1 t equal to u 1 t plus alpha 2 u 2 t divided by 1 minus alpha 2 beta 1. So, you get this value. So, you get this equation, and in this equation in the right hand side P t is not involved, and then you can substitute this value of W t in any of those two equations, and then you obtain P t equal to pi 2 naught plus pi 2 1 u t plus pi 2 2 r t plus pi 2 3 m t plus V 2 t, where these are the values of pi 2 naught, pi 2 1, pi 2 2, pi 2 3 and V 2 t. Simply what you have to do is you take this value of W t or this, and then you substitute this value of W t in this equation or this equation, and then you solve it for P t. So, ultimately you get this equation. Again in this equation also you have just one endogenous variable, that is P t. So, this is your original structural form, and then you have transformed it or you have solved it for W t and P t, so that each equation has just one endogenous variable. So, you get this equation involving just W t, and you get this equation involving only P t. So, these are the reduced form of the model. Then is it possible to estimate the reduced form coefficient, and then with the help of those estimates estimate the structural form coefficients? Now, notice that in this reduced form you do not have the problem of correlation between exogenous variables and the disturbance term, or you can say explanatory variables and the disturbance term. So, you can easily apply the OLS procedure for estimating pi 2 naught, pi 2 1, pi 2 2 or pi 1 naught, pi 1 2, pi 1 1 etcetera. So, you can estimate all the pi's using the method of least squares. Then the question is, after estimating pi's, is it possible to solve such all these equations so that you get solutions for alpha naught, alpha 1, beta naught, beta 1, alpha 2, beta 2 etcetera, or is it possible to estimate the structural form coefficients with the help of estimates of reduced form coefficients? Then Now, we discuss some examples to explain different problems that arise in the analysis of a simultaneous equation model. Now, first we consider the following consumption function with a national income identity. So, you have this consumption function C t equal to alpha plus beta y t plus u t, and then y t is equal to C t plus Z t. Here C is the aggregate consumption expenditure, Y is the national income, Z is non-consumption expenditure, and U is the disturbance term. So, in this model, consumption expenditure is a function of national income. So, on the right hand side you have national income. Then in the second equation, using this income identity, you are determining the national income. So, both the aggregate consumption expenditure as well as national income are jointly determined by the interaction of equations of the model. Simultaneously, these two equations are determining C and Y. So, the model determines the consumption expenditure and the national income, and these two variables are the jointly dependent or endogenous variables. So, the model has two endogenous variables. Again, in the second equation you do not have any parameters. So, there is no problem of estimation, you do not have to estimate any parameter. In the first equation, one can think of applying OLS procedure for estimating alpha and beta. So, this model contains a behavioral equation 1 and equilibrium condition 2. Then this equilibrium condition have no disturbance term, and this second equation is exact. So, you do not have to estimate any parameter in the second equation. Further, this variable Z, which is non-consumption expenditure, is determined outside the model, which makes it exogenous variable. Now, suppose we assume that U follows a normal distribution, normal 0 sigma square U I n, where this U is equal to U 1, U 2, U n transpose, and Z and U are independent. Obviously, Z is exogenous variable. So, you can assume that Z is uncorrelated with U. Now, we solve these two equations for C and Y. So, the first equation is C t equal to alpha plus beta y t plus u t, and then y t is equal to C t plus Z t, and then we substitute the value of y in the first equation. So, you get C t equal to alpha plus beta C t plus Z t plus u t, and then we take this term involving C t towards the left hand side. So, you get 1 minus beta C t equal to alpha plus beta Z t plus u t, or C t is equal to alpha upon 1 minus beta plus beta upon 1 minus beta Z t plus 1 upon 1 minus beta u t, and then we write V t equal to 1 upon 1 minus beta u t. Then 1 upon 1 minus beta u t follows normal distribution, it has mean 0, and variance is 1 upon 1 minus beta square sigma square u. Similarly, you can get the value of y also. So, y is equal to c plus z, then we substitute this value of c here. So, you get alpha upon 1 minus beta plus you have beta upon 1 minus beta z here, and then you have one more z here plus 1 upon 1 minus beta u t, and then we solve it for y. So, you get alpha upon 1 minus beta plus beta upon 1 minus beta plus 1 is equal to 1 upon 1 minus beta z t plus 1 upon 1 minus beta u t is equal to v t. So, you get this equation for y. So, this is the reduced form. Now, probability limit of 1 upon n summation y t v t is equal to probability limit of 1 upon n summation, you write y t equal to alpha upon 1 minus beta plus 1 upon 1 minus beta z t plus v t into v t. Then the probability limit of 1 upon n summation v t is 0, because v t's have expectation 0. So, this tends to 0 in probability. So, the first term has probability limit 0, then the second term has summation z t v t, and then you are dividing by n. This also has probability limit 0. So, finally, you obtain probability limit of 1 upon n summation v t square. Then 1 upon n summation v t square converges to its expectation. So, you get sigma square u upon 1 minus beta square, and then this is not equal to 0. So, in probability limit y t is correlated with v t. Now, this is the problem. In fact, y t is also correlated with u t, because v t is simply equal to 1 upon 1 minus beta u t. So, you can easily verify that y t is correlated with u t also. If we apply the OLS procedure to equation 2, then the resulting estimators are actually, you have this equation, and if you directly apply the OLS procedure, then the estimator of beta is beta hat equal to summation C t minus C bar y t minus y bar divided by summation y t minus y bar whole square, and the estimator of alpha is C bar minus beta hat y bar. Then, because of the correlation between y t and u t or y t and v t, these estimators are inconsistent. So, you require some alternative estimation procedures. Now, one of the procedures which we considered in case of measurement error models also is instrumental variable estimation procedure. Now, here you have a variable z which is uncorrelated with u, and it is correlated with y. Ultimately, y is equal to c plus z. So, z and y are correlated. So, you can use this variable as an instrumental variable. So, now we apply instrumental variable estimator using z as the instrumental variable. Then you obtain instead of y t, now you are using z as your instrumental variable. So, your instrumental variable estimator for beta is BIV equal to summation CT minus C bar, and you have ZT minus Z bar here, divided by summation YT minus Y bar into ZT minus Z bar. And then the instrumental variable estimator for alpha is say AIV equal to C bar minus BIV Y bar. So, you just take this Z as the instrumental variable. So, you get these instrumental variable estimators, and suppose you write CT minus C bar equal to small ct and ZT minus Z bar equal to small zt, and then we write YT minus Y bar equal to small yt. So, these small ct, small yt and small zt are the deviations from respective means. Then we can write summation CT ZT as, say, you substitute the value of CT here, the equation is CT equal to alpha upon 1 minus beta plus beta upon 1 minus beta ZT plus VT. Then we take deviation from mean CT minus C bar, this is equal to, so this term vanishes, you get beta upon 1 minus beta ZT minus Z bar plus VT. So, you write small ct equal to beta upon 1 minus beta ZT, you take capital ZT minus Z bar equal to small ZT plus VT into ZT. So, you get beta upon 1 minus beta summation ZT square plus summation VT ZT. Then in the denominator we have summation YT ZT. Again we write the value of YT from equation 4. You write this value of YT. So, you get summation YT ZT equal to summation 1 upon 1 minus beta ZT plus VT into ZT. Then you obtain 1 upon 1 minus beta summation ZT square plus summation VT ZT. Then probability limit of 1 upon n summation CT ZT is equal to, you get beta upon 1 minus beta, then we write n ZZ equal to probability limit of 1 upon n summation ZT square. So, if we divide this equation by n, you divide both sides by n and then you take the probability limit, then probability limit of this term is equal to 0, and here you get n ZZ. So, finally, you obtain probability limit of 1 upon n summation CT ZT equal to beta upon 1 minus beta m ZZ. Similarly, you can obtain the probability limit of 1 upon n summation YT ZT, and it is equal to 1 upon 1 minus beta m ZZ. You get this result, probability limit of 1 upon n summation YT ZT equal to this. Now, we obtain the probability limit of BIV. Remember, BIV is equal to summation small ct ZT divided by summation YT ZT. Then we divide both numerator and denominator by n, and then we take the probability limit of BIV. So, the probability limit of this numerator is beta upon 1 minus beta m ZZ, and the probability limit of this denominator is 1 upon 1 minus beta m ZZ. So, finally, you obtain beta. So, the probability limit of BIV is equal to beta, and then the probability limit of AIV is equal to actually A I V is equal to C bar minus B I V y bar. Then we write C bar equal to 1 upon n summation C t and y bar equal to 1 upon n summation y t. So, probability limit of A I V is equal to probability limit of 1 upon n summation C t minus B I V y t, and then C t is equal to alpha plus beta y t plus u t. So, we get probability limit of 1 upon n summation alpha plus beta y t. So, we adjust beta here plus u t, and then you have B I V y t here. So, you get minus B I V minus beta y t here. Now, the probability limit of B I V is beta. So, this part converges to 0. Further, the probability limit of 1 upon n summation u t, this is also 0, and then 1 upon n summation t equal to 1 to n alpha is equal to alpha. So, you get the probability limit of A I V equal to alpha. So, now both A I V and B I V are consistent estimators of alpha and beta. Then using the same example, we explain the method of indirect least squares. In the method of indirect least squares, what we do? We apply OLS to reduced form equations. Now, these are the reduced form equations, and these reduced form equations satisfy the conditions under which OLS estimators are consistent and best linear unbiased estimators. So, applying OLS to these reduced form equations is not a problem. You can estimate the parameters using the method of least squares. Then the consistent estimator of beta upon 1 minus beta, this parameter is, say you estimate beta upon 1 minus beta by summation C t minus C bar Z t minus Z bar upon summation Z t minus Z bar square, or you can write it as summation small c t small z t upon summation small z t square. So, this is a consistent estimator of beta upon 1 minus beta. Similarly, from the second equation you obtain a consistent estimator of 1 upon 1 minus beta as summation y t minus y bar z t minus z bar divided by summation z t minus z bar square, or you get this consistent estimator of 1 upon 1 minus beta. So, you have obtained the consistent estimators for the slope coefficients of reduced form equations. Then using these two estimators, you can obtain estimator of beta. So, you take ratio of these two, say beta divided by 1 minus beta divided by 1 upon 1 minus beta is equal to beta. So, this is the relation between reduced form coefficients and the original structural parameter beta. So, you can estimate beta as a B I L S equal to, you divide summation C t z t divided by summation z t square by summation y t z t divided by summation z t square, and then you get this estimator. So, in the method of indirect least squares, how we proceed? We estimate the reduced form coefficients using the OLS procedure. We have applied OLS to estimate the reduced form coefficients, and then we look at the relationship between the original structural parameters and reduced form coefficients, and using those relationships we estimate the original structural coefficients. So, original structural coefficients are estimated by an appropriate transformation of the estimates of reduced form coefficients. So, for example, here we have divided the estimator of this reduced form coefficient by the estimator of this reduced form coefficient, and then we get the estimator for beta. So, this is the method of indirect least squares. Now, we consider the method of two-stage least squares. Now, in the method of two-stage least squares, we first regress y on the exogenous variable. So, in the model you have the exogenous variable z apart from the interceptor, and let us take the observations as deviation from mean. So, we write the second equation as small y t equal to delta z t plus v t. So, delta is equal to 1 upon 1 minus beta. So, you have this equation. Then we run regression between y and all the exogenous variables, means y and z. The OLS estimator of delta is now delta hat equal to you have summation y t z t divided by summation z t square. So, you get this estimator of delta. So, this is the first step. What we do? We consider all the exogenous variables available in the model, and then we regress y on all the exogenous variables. In the next step, we obtain an estimated value of y. Say y t hat is equal to delta hat z t. So, this is the predicted value of y or estimated value of y. We substitute the value of delta hat here, and then you can easily verify that summation y t z t upon summation z t square is equal to delta plus summation v t z t upon summation z t square. You simply substitute the value of y t here into z t. And if you take summation y t hat u t, this is equal to delta summation z t u t plus summation u t z t summation v t z t divided by summation z t square. And then we take the probability limit of 1 upon n summation z t u t, which is equal to 0. Similarly, the probability limit of 1 upon n summation z t v t is also equal to 0. And this shows that if you take the probability limit of 1 upon n y t hat u t, then we obtain the probability limit of 1 upon n summation y t hat u t. So, we divide both sides of this equation by n, and then we take the probability limit. Now, the probability limit of this part is equal to 0, probability limit of this part is also equal to 0. So, finally, you obtain the probability limit of 1 upon n summation y t hat u t equal to 0. So, in probability limit y t hat is uncorrelated with the disturbance term. Now, we write the first equation of this 2 as C t equal to alpha plus beta y t hat plus u t plus beta y t minus y t hat. So, we are writing y t equal to y t hat plus y t minus y t hat in the first equation of this 2, and then we get this equation. Then y t hat has 0 correlation in limit with u t, and then y t hat also has 0 correlation with y t minus y t hat. So, y t hat has 0 correlation with the combined disturbance term this u t plus beta y t minus y t hat in equation 8. So, since y t hat has 0 correlation in limit with this term, this is the combined disturbance term. So, you can apply OLS procedure for estimating beta here. So, if we apply OLS procedure to this equation, this gives the two stage least square estimate of beta, which is a consistent estimator, and the estimator is say B 2 SLS equal to summation C t y t hat. This y t hat is actually capital Y t hat minus y bar divided by summation y t hat square, and then we substitute the value of y t hat. Y t hat is equal to delta hat z t. So, you get delta hat summation C t z t divided by delta hat square summation z t square, and then we get summation C t z t in the numerator. In the denominator, you have delta hat summation z t square, and then we substitute the value of delta hat here. Delta hat is equal to summation y t z t divided by summation z t square, then you have into summation z t square. So, ultimately you get summation y t z t in the denominator. So, this is the two stage least square estimator. Now, in this particular example, all the three estimation procedures, the instrumental variable, the indirect least square and two stage least square, lead to the same estimator. In general, it is not true. In this particular example, it is just because all the equations are just identified, although so far we have not discussed what is just identified. But in this example, this is the reason why all the three estimation procedures lead to the same estimator. Now, in many economic applications, the data generating process involves a set of variables which are jointly determined by a set of equations. So, your model is not a single equation model, it is a set of equations, and these equations or such kind of models are called simultaneous equation model. A special thing about these models is that each equations may have more than one endogenous variables. Then the problem arises that some of the variables towards the right hand side, which are endogenous variables, are correlated with the disturbances. So, as such you cannot directly apply the OLS procedure. So, in this lecture we have discussed an example, and with then we have used three estimation procedures. We have explained three estimation procedures: the instrumental variable estimation, the indirect least square and two stage least square with the help of that example. In next lecture, we will consider the general simultaneous equation model and then different problems which we face in simultaneous equation model. So, I am going to stop here. Thank you.
I am A.K. Sharma and I am professor of sociology at IIT Kanpur. The question I am going to address is what is urbanization? Urbanization is essentially the process of population concentration, which means that if more people start living in a smaller number of places or if the distribution of population becomes more unequal, like more people living in places like Bombay, Calcutta, Mexico, then we say that the urbanization is taking place. Essentially, it means increase in percentage of population living in areas or localities which are defined as urban. Urbanization is a new phenomenon, of course, a post-industrial phenomenon. About 200 years ago, hardly 5% population of the world lived in urban areas, and today more than 50% population of the world is living in urban areas or localities which are classified as urban. You will be happy to know that according to 2011 census of India, in our own country for the first time, increase in the urban population has been greater than the increase in the rural population, though India is not so urban as the developed countries, and about 31% population of India only is living in urban areas. We can believe that in 10 years, 20 years, 30 years time, India will also be more urban, at least more urban than what it is. It may not be 80%, but certainly it will be 35% or 40%. Now, how is this urban locality defined? Because this definition of locality as urban or rural is crucial to measure level of urbanization. I will give you definition of our own country. In Indian census, an urban locality is defined in two ways. There are statutory towns and there are census towns. All places with municipality, municipal corporation, cantonment or notified town area committees are called urban. This is statutory definition. According to demographic definition, there are three main criteria. If a locality has more than 5,000 people or 75% of male labor force is engaged in non-agricultural activities, or the density of population is 400 per square kilometer or 1000 per square mile, then we say that the locality may be classified as urban. There are many other additions to this definition. Now, we have the concept of urban agglomeration and many other things, but essentially this is how urban population is defined in India. And as I said that urbanization is associated with economic development and industrialization, same is the case with India. About 100 years ago in India, only 11% people were living in urban areas. Today 31% are living in urban areas, and this is obviously linked with economic development of the country, growth of per capita income and industrialization. I remember that in one 5-year plan it was mentioned that today this urban population can grow by way of natural increase of births minus deaths in the urban areas itself or through rural to urban migration. Today nearly 60% contribution to growth of urban population is due to rural to urban migration, and this is going to increase. This is essentially what urbanization means. Urbanization means growth of population in localities defined as urban in relation to population of localities defined as rural, and I have given you Indian definition. Thank you very much.